Hi and welcome to this lecture 18 on machine learning. In this lecture we will conclude our discussion on logistic regression and also introduce neural networks. Recall our extension of the binary logistic to the multi-class case. Imagine that we have k classes, so one extension to k classes is as follows. We are going to have a weight vector wc1 to wcp, a p dimensional weight vector for each class C. But we are going to do this for the first k minus 1 classes, and the probability of a class C is nothing but e raised to minus wc transpose phi x divided by 1 plus summation of this factor over the k minus 1 classes. For the kth class we just have a 1 in the numerator. This is like setting wk to 0 so that e raised to minus wk transpose phi x is nothing but 1. So this way we are kind of saving parameters for the kth class. One can however be a bit more lenient in parameterization and have classes and weight vectors for all the classes. So here is the weight vector for the cth class, and we are going to do this for all the k classes. The term is almost the same as before, except that for the kth class we do not have a 0 weight vector, and therefore the factor 1 has disappeared. Now I claim that the probability distribution provided by this new equivalent extension is the same as the probability distribution provided using the previous formulation. So the family of probability distributions using the alternative formulation is the same as the family of probability distributions using the first formulation. Now one will have to prove this both ways. I have already shown that the family of probability distributions using the first formulation is a special case, is an instance of the family of probability distributions using the alternative formulation. So let us call this 1 and this called 2. So the fact that 2 is a subset of 1 is evident as follows. Set wk to 0 as we did before, and this should show that 2 is, every instance of 2 can be recovered from 1. How about the other way? We want to prove that 1 is also a subset of 2. Well, that is also not difficult. The clue is to divide the probability of y equals c given phi x by a single expression, and that is e raised to minus wk transpose phi x. So this will mean that the new distribution or new weight vectors we will get for every class C, wc tilde will be nothing but the old wc minus wk. One can verify that dividing the numerator by e raised to minus wk transpose phi x and doing the same for the denominator, e raised to minus wk transpose phi x will just mean that you are going to subtract wk from wc in both numerator and denominator. In denominator, of course, you will have one of the wk's disappearing or cancelling out against this wk, the one corresponding to the kth class. So we more specific, we should capitalize this k. We mean the specific k corresponding to the last class. One can also come up with an alternative representation for logistic regression using the kernel, and this basically can help us deal with very large dimensional feature spaces. So recall the regularized cross entropy loss function. One can rewrite this, we have shown this is possible, as EW is minus of 1 upon m summation I equals 1 to m of yi W transpose phi xi, the error component that looks similar to the perceptron, plus log of 1 plus e raised to W transpose phi xi. Of course, we will also have the regularization 1 upon lambda by 2m norm W square. Now one can further simplify this, set the gradient to 0, but one can actually make use of some matrix equalities to come up with the following formulation. The dual form, which is equivalent, has this kernel kxixj times alpha j multiplied by yi. So log of fwxi has been substituted by a summation over j of kxixj alpha j. Similarly, well, this is not just about the first term, but this happened also with the second term. So all this is easier to realize if you look at the formulation that we recalled. So it's easy to see that this component has been replaced by the summation over j of kxixj alpha j. One will also get the quadratic component by virtue of the regularizer, and finally the term dealing with log, which is independent of yi, continues remaining so. So the homework problem for you will be to show this equivalence. You can make use of the hints, the form of these correspondences that I have pointed out. The decision function is basically 1 by 1 plus summation over j of alpha j k x comma xj, and again note that this has taken the place of e raised to minus W transpose phi x. So we are going to look at the multi-class logistic regression and generalize it to settings where there is structure on the output space. And we are talking about the output space Y. A very canonical example is that of part of speech tagging. So consider the following two sentences. I would bank upon him for a solution, as against I visited the river bank. Now I know that the bank talked about in the first sentence is a verb, and that in the second is a noun. In fact, I could come up with the part of speech tag sequences for each of these. For the first case, it would start with a pronoun and so on, a verb, a preposition, pronoun and so on. In the second case, it will be a pronoun, a verb, article, a noun and a noun. So, would the fact that the word immediately preceding the verb in the first case, bank in the first case, actually happens to be an auxiliary verb. So, would the fact that would is an auxiliary verb help you understand bank to be a verb, whereas in this case the river is a noun, and therefore would that help you figure out that this bank is a noun? So, in these cases we want to make prediction on the entire output at once. Toward this, can we reformulate and generalize this logistic regression formulation? So, what we are going to do is try and make phi a function of the class, and this is how we will do it. This is nothing but e raised to minus some new w tilde transpose phi x comma c divided by summation over all the classes of e raised to minus wk transpose, but now instead of wk I will have w tilde transpose phi x comma k. What have I done? Well, I had a series of vectors w, w1, w2, w3. So, w was essentially a matrix here. I am now trying to serialize that matrix and come up with a vector representation for w. So, at the price that I am paying is that I am making phi an argument of c. So, specifically this w tilde will mean that each subsequent row of the w matrix is appended to all the previous rows. The price that we pay is that we will have to make phi of the same dimension as that of w tilde. So, w tilde will be a p into k dimensional vector, phi should also be of the same dimension. What will the components of phi look like? Well, it will be phi x repeated one after another, but only that phi x will be instantiated which corresponds to the class that y is. Specifically in this setting we expect that when y is c, then delta yc is 1, because delta ab is 1 if and only if a equals b and 0 otherwise. So, delta yc will be 1 and therefore this phi x gets instantiated. So, this equals phi x if y equals c, and on the other hand all the other components in phi xy will be 0 when y equals c. So, one can easily convince oneself that this new formulation with w tilde and phi viewed as a function of two arguments is the same as the previous formulation. Now, all this was so that we could deal with non-trivial y's. So, here is an example in the case of conditional random fields, and recall the problem of part of speech tagging where you have word 1, word 2, word n. These would correspond to x's, x1, x2, xn, and what you are interested in is the part of speech tag for 1, the part of speech tag for 2 and so on, part of speech tag for the nth word. This can be modeled by looking at probability that y is a particular part of speech tag sequence given the word sequence w1 to wn as follows: e raised to minus W tilde transpose phi, the W vector comma the specific pos vector divided by Z of the word vector with the weight vector. Now the Z can be slightly messy to handle because the Z will involve summing over all possible output configurations. So the disclaimer here is Z can be messy or non-trivial to compute, involving summation over lots of output configurations. So more generally, probability of y given x is e raised to minus w transpose phi x comma y divided by z x comma w. So we are modeling the entire output vector y jointly. Conditional random fields are very special examples of such a joint modeling, where we consider very special forms of phi. So we have an input sequence x1 to xn, output sequence yn to yn. We are going to consider some specific phi's that are a function of specific inputs and specific outputs. So phi 1x is a function of the first component of input x and the first component of output y, and so on. We also have phi's which are functions of two successive outputs. So it's phi y1 comma y2, similarly phi y2 comma y3, and so on. As an example, you do not expect certain part of speech tag sequences to follow certain other parts of speech tag sequences. So you are not expecting an adjective after a noun unless there is some punctuation. So you might encode a feature phi nn comma jj, noun comma adjective, and the weights corresponding to this you expect to be highly negative. You will expect this to be very negative. Basically you want to discourage prediction of such highly improbable part of speech tag sequences. More about this in the notes with the link provided below. Going back to our discussion on perceptrons, we have already seen the kernelized perceptron. We have seen also the kernelized logistic regression formulation. These give you nonlinear separation. Another way to go about this is through neural networks. So there are settings where you really do not know how to design the kernel functions. So neural networks achieve the same nonlinearity, or probably with more computational ease, through cascades of layers of perceptrons, and this gives you nonlinearity. So the sign of W transpose phi x can be replaced by any one of the following activation functions. You could look at the simple linear function with a step, the sigmoid function we have already discussed. You could also look at rectified linear unit, which is GSS max of 0 comma s, and this rectified linear unit basically looks like this. So it is going to be 0 for all negative values of s, and thereafter it is linear, a 45 degrees angle. An approximation to the rectified linear unit, that is differentiable everywhere. So the soft plus function gs equals ln of 1 plus e raised to s. So this, beg your pardon, this should be e raised to s, and this looks as follow. It can never be negative. However, while it is always above the pink line, at infinity it tends to merge with the pink line. So it is an approximation that is differentiable everywhere. On the other hand, the ReLU unit is continuous but not differentiable at 0. The last three options, 2, 3 and 4, we do not do any thresholding right away. The thresholding step is deferred. In fact, there is a connection between the bias term that is employed, often buried or hidden into phi, and the thresholding term theta. So one can look at simple Boolean functions and model them using linear separators. So here is an example, your function x or y. One can convince oneself that this simple perceptron gives you separation x equals 0 and y equals 0, implies that you are looking at 0 plus 0 minus 2.5, which is certainly less than half, so which means that the output should be 0. X is 1, y equals 0, and in fact the same holds for x is 0, y is 1. You get 1 plus 0 or 0 plus 1 minus 0.25, which is indeed greater than half. So the output will be 1 as expected, and obviously for x equals 1, y equals 1, you do get 1 plus 1 minus 0.25, which is indeed greater than half. So the output is 1. One can similarly convince oneself that x and y is modeled by a similar perceptron but with modified bias term b. It is minus 1.25, the threshold has been made more negative. One can also do not using perceptron. Here you have x multiplied by a negative weight minus 1. How about XOR or exclusive OR? So recall that exclusive OR is 1 if either x is 0 and y is 1, or x is 1 and y is 0. One can actually plot XOR. So the positive points will correspond to x is 1, y is 0, or y is 1, x is 0. The negative points will be here, x is 0, y is 0, x is 1, y is 1. Now it is impossible to have a linear separator between the positive and the negative points. One can see that the following two linear separators, a combination of the two can give you some separation. So you get this positive region and the following negative region, which is what was expected. So how about doing the following? How about modeling the first component using a perceptron? Well, you will need to do a knot using another perceptron. It is however possible to do a knot x and y using a single perceptron, another perceptron for x and not y, and doing a third perceptron to combine these two using an OR. So that is the idea behind feed forward neural networks. You have a cascade of activation functions, z1 is g times the summation, the weighted linear combination of inputs obtained from the previous layer, z2 is again another activation function, and then you finally combine these. You can keep doing this for multiple layers. What you see here is a final output layer. You could have multiple outputs. Let us try and illustrate the feed forward neural network for XOR. So in the case of XOR, I let one neuron or perceptron handle the case of one conjunction, the other neuron take care of the other conjunction, and a third neuron take care of the disjunction. One can of course also express the whole thing as disjunction and then conjunctions on top. So one can easily convince oneself that this particular 3 node perceptron neural network will actually give you the XOR function. We will leave it as a homework for you to evaluate the inputs, the 4 possible inputs on this neural network. In the next lecture we will build upon this example. Thank you.